if you well, but then it is that's exactly. So this is exactly extremely explicit. So we didn't see inject it next to you. So actually we absolutely not use to go because then you have exactly the same. Then your cross section has nothing to do with it. It's actually a cross section which is completely by the QCD. And that's so you cannot use a word. You have to use the same yeah. But you know that the third jet is so the third jet is always below the okay. So you don't allow shower. Too high. That's right. So right. Yeah. So then. That's also why we saw it. Right. So why do you need to know that? Just to make sure that more recent. Since it's a shower, it will always be lower. Than yours. So you should have very small. It should be
Welcome everybody to class. I am called Tagira from KK with Zilpen here for the month. And I would like to tell you that this is actually the second MGraph school I organized. And the first one was in 2006, 5 years ago, when we organized our first school at KK, and Professor Johan Auer was the lecturer there, and we were very happy. And I do remember that at that school, maybe the size of the student is maybe half or one-third. I don't remember, it was a much smaller room. But from there, you know, this is like Kentaro Mawatari and Hiroshi Yokoya, who's Kentaro is now in Brussels, and Hiroshi Yokoya is now in Taiwan National University, and I think Chan Lee is now in Beijing, right? And they came out of this our first school, and now the LSE started, and I think that we really need many students to be accustomed to those tools to simulate LSE physics. Because without tools, actually, LSE physics is so complicated. Without tools, it's very difficult. But once you master those tools, I think you can really enjoy LSE physics. And
tomorrow I will talk about the same thing that I talked about at KK 5 years ago. So those of you, no, nobody was from this group was there 5 years ago. No one will recognize some of the things I'm saying. Anyway, so I will give the first 2 lectures this morning, and then Olivier will give the last lecture, which is the true introduction to MGraph. So I will give an introduction to event generation in general. So in the first lecture, actually, is there one?
Yeah, there. Look on the right, left for you.
Ah, good, strong point. In the first lecture, I will talk a little bit about why we're here, about the LHC. I will give some introduction to QCD, just to make sure that everybody has seen this at least once. Probably you have all done this in quantum field theory course, but you might not have seen everything that I'm showing you. And I will introduce Monte Carlo integration and Monte Carlo generation, and what is the difference between these two. In the second lecture, I will talk a little bit about complete collider event simulation. I will talk about pattern showering and jet matching, just to give a very short introduction to what you will hear much more about during this school. And I will give you a direct demonstration on my laptop for how to simulate events using MGraph. Then, in the third lecture, Olivier will take over and discuss more technical details about MGraph. So the idea is to get you acquainted with the concepts and techniques that are used in event simulation, event generation, to give you some hands-on experience with matrix element generation, event generation, and analysis, in particular during the tutorial, of course. And I'm very open for you to ask questions. This is a school. It's not a conference, it's a school, so please feel free to interrupt me at any time and ask questions. If I don't ask you to ask me, just interrupt if you have any questions. So, why over here? What's all the buzz with the LHC? Well, the main point to my way of viewing this is the Higgs boson. The Higgs boson has a natural mass which is at the scale of whatever new physics is out there, and the only new physics that we know from the point of view of quantum field theory is the Planck mass, so gravity. The standard model, however, it only works if the Higgs boson mass is down here, close to the electroweak scale. And the reason for this is that any new physics that we have at some higher scale is communicated, the scale of this new physics is communicated to the Higgs boson through quantum loop contributions to the Higgs mass. So the change in Higgs mass due to loops like this are proportional to the mass squared of new physics. So the easy way to solve this is to just do a renormalization. So you cancel whatever this contribution is by having a bare mass term. The problem is just that the new physics contribution we saw was up here. The bare mass term should be down here, so we'll have need a cancellation which is to the order of 10 to the 34 or something like that. So if we don't accept that kind of cancellation, if we believe that the theory should be natural, as it's called, then we need to introduce new physics somewhere much closer to the weak scale. So if we want a fine-tuning which is less than 1%, then we need new physics which cuts off these quadratic loops at around 1 TeV. So this is really the core reason to build the LHC at 14 TeV, because you are safely covering the 1 TeV region of mass. So together with dark matter, the fact that we have seen dark matter in the universe, and to some extent grand unification, which is a very beautiful theoretical idea but doesn't have this type of direct implication on the theory, these three problems, or mainly these two problems, have been driving new physics model building in the past 30 years. So dimensions, also called Randall-Sundrum, little Higgs theories, and a huge number of variants and combinations of these different fundamental ideas, which have been that we can simulate, and we can see what the effects of these different ideas would be at the LHC. And if we're really lucky, then we might also find something which is completely unexpected and does not come in any of these different categories. So what has happened recently? Well, the LHC has taken over from the Tevatron. The Tevatron is now officially dead since almost 1 month. We have very significant luminosities that have been and are being collected. So the Tevatron collected over 10 inverse femtobonds during the last 10 years, so since 2001 or so. And the Tevatron really has an amazing legacy, an amazing amount of data that still hasn't been fully analyzed, of course. And it has several quite interesting excesses, including the top forward-backward asymmetry and some other interesting accesses. I will talk about one of them. The LHC, if we look at this, Tevatron got 10 inverse femtobonds in the last 10 years. The LHC only started running for real last year, and we already have a spectacular 5 inverse femtobonds. So they already have half as much luminosity as the Tevatron during the 10 years. It's really spectacular. And by the end of 2012, which will be the end of the present run of the LHC, we might have as much as 20 inverse femtobonds. So we might have doubled the data set of the Tevatron at a much higher energy. So this really allows us to stringently test the standard model. So if we now see some excesses about the standard model background, well, how do we interpret them, and how do we determine that they are really excesses? The answer is, to a large extent, Monte Carlo simulation. So what we will talk about at this school is really the core of how to do LHC physics. The reason is that the data is so complicated, these events are so complicated that there's no way we can make sense of them using only fundamental basic theory. We really need the Monte Carlo simulation, which can generate the complete events which look like complete LHC events. Then, of course, especially for standard model backgrounds, for the experimentalists, also data-driven methods. So just using data in sideband and extrapolating the data is also a very important method to determine standard model background. So a very nice example of this, which is also an example of completely unexpected new physics, if it is new physics, is the CDF excess. So CDF is one of the 2 experiments at the Tevatron, and they found a very interesting excess in W plus 2 jets. So something like this. This shows the invariant mass of the 2 jets after subtracting all backgrounds except for this background, which is W plus W minus generation, where the W minus goes to a muon, or one of the W's goes to a muon, the other W goes to 2 jets. So this gives a peak when the invariant mass of these 2 jets after W mass.
Yes, yeah.
Okay.
Bucket or close it?
I think that is my alarm. Very good.
I try to close it.
Thanks. It's in the front pocket. Okay. So this, we can clearly see this, the W peak, the invariant mass of the W and the C here around 90 GeV, where it's expected. But they also see a second peak around 140, 150 GeV. And nobody knows what that peak might be. So this is a very interesting example of possible new physics. However, if we really look closely, as I said, this was a background subtracted plot. And it's in the front pocket.
And this one?
Yes.
Okay.
Sorry about that. Very good. You might want to do this.
Yeah.
So as I said, it's a background subtracted sample. So what background they have subtracted is something that's very important. So this shows the picture including the standard model backgrounds as they show up from simulation. So we have the CDF data here, and then we have the standard model backgrounds. And these backgrounds, the normalization is given by the data, but the shapes are all given by a simulation. So we have the shape, you can see that we have the WW background here in red. We have the W plus jet background, it's the big green one here. Then we have the top, T plus jets, and some residual QCD background. And as you can see, the main background here is W plus jets. And W plus jets is a very important, extremely important channel that we will see a lot more of in the next few days. I believe both me and Gregory will talk a lot about W plus jets. So if we get the shape of the W plus jets background wrong, or if we get the shape of the top background wrong, then we can easily account for this excelsior. So the main point here is that in order to interpret the physics that we have at the Hadron Collider, we certainly need to know our backgrounds very well. So before we start doing anything else, we need to understand our processes. The cross-section for a given process at the collider, it depends on a few different important aspects, and it's important to keep all of these in mind when you think about backgrounds and signals for new physics. So the coupling string, of course, how strongly it couples to the standard model particles. What it couples to. If we, for example, have some new state which couples only to electroweak gauge bosons, or if we have something which couples only to leptons, we'll have a very small cross-section compared to if they couple to gluons, which is the main component of the colliding protons and antiprotons. It depends a lot on the mass, as mass to the power -4 or so. And it depends very much on whether the new states are singly produced or pair-produced. So here we see the standard model, a set of standard model processes, and how the cross-section evolves from the tevatron to the LHC. This is the 14 TeV LHC here. And the expected new physics would be in this range. Of course, you can continue down as far as you want, but the expected new physics that we might be looking for at the LHC would be in this range. So the master formula for physics at the LHC is the following. We start out with the Potten level cross-section, which comes from a matrix element. Then we have the Potten density functions, which are process independent and depend only on the type of the particle, A and B. So A and B can be quarks or gluons. Then we need a phase space integral. And here we have the S hat, which is x1 times x2 times x. So x1 and x2 are the momentum fractions of particle 1, particle A and B. So the main difference, as you can see here, the only difference between different types of colliders, as I said, it's snoozy, so you need to turn off the line. Thanks. The main difference between different colliders are given by the Potten luminosity, so only this part. The rest of it, it's collider independent. So if we now compare the two colliders, the two important colliders of our time, meaning the last 10 years, we have the tevatron and we have the LHC. The tevatron is dead, so we don't have it. Tevatron is a 2 TeV proton-antiproton collider. It never quite reached 2 TeV, but close enough. And in a proton-antiproton collider, the most important is QT bar annihilation. So for QT bar production, this is 85% of the cross-section. At the LHC, we have protons colliding on protons, so QT bar annihilation is not as important. The most important thing is actually glue annihilation. So this is 90% of QT bar at the LHC. here we see a snapshot of Hotton densities for a given scale, factorization scale. We have the up, down, then we have the gluon, which has been scaled down by a factor of 10. So you need to scale up the gluon contribution by a factor of 10. So actually it's up here already at Q times 10 to the minus 2. And then we have the bottom quark, which I include because bottom is the only quark in the proton which couples directly to Higgs, for example. So we can see that we have a very strong dependence on the type of quark, or if we have a gluon, when it comes to how much, which cross section we can get for a given process. So if we compare the LHC and the tevatron and look at the ratio of Hotton luminosities, we see that glue is really by far makes the biggest difference between the LHC and the tevatron. So for LHC, we'll have a huge cross section, although still at very large masses. So this is the mass of the new produced state. However, for a low mass state, the tevatron is a better discovery machine because the backgrounds are much smaller. The backgrounds are typically QCD, and the background scale as the glue. So if we now look at our standard model processes, and we map them onto this this ratio plot between tevatron and the LHC, we have B production, so that's down here. So we see that it doesn't increase very much when we go from tevatron to the LHC. We have Z production here, so Z is produced from QQ bar. So we also don't have a very large increase from the tevatron to the LHC. And if we look at top is gluon fusion mainly, so we have a huge increase going from the tevatron to the LHC. So we really need to understand our process to fully appreciate how they change between different colliders. So now if we want to calculate the matrix element at a hadron collider, say we want to calculate PP goes to TT bar, then we have 3 steps that we need to do. We first need to determine the contributing subprocesses. So in this case, it's glue to TT bar, QQ bar to TT bar, and Q bar Q to TT bar, where Q and Q bar are DUSC quarks. Then we need to determine the matrix element for each subprocess. So the matrix element, as you know, is the sum of Feynman diagrams, and then you square the sum. And finally, you need to perform the phase-space integration for each subprocess. So it's this part. So the first part here might seem easy enough. That's fine. Determining the matrix element, well, in this case, TT bar is not that difficult, but in general, it's quite hard. And finally, performing the phase-space integration, which, at least in my quantum field theory course, we kind of stopped at the matrix element. But actually, this is by far the most difficult thing to do by hand. So in general, it's very hard. So in the next section, I will talk about a little bit about the matrix element, or actually what I will talk about is QCD. And in the section after that, I will talk about how to do this phase-space integration. So minimal QCD basics. Here I will try to get the main properties of QCD from just starting from the properties of QED and then adding the one more component that differs between QED and QCD. So in QED is an abelian theorem. The Lagrangian looks like this. So we have the kinetic term for the photons. We have the kinetic term for the electrons, and then we have this interaction term. And this field strength here is given by this. So the Feynman rules are these. So we have the propagator for the electron, we have the propagator for the photon, and we have the interaction term, which is just the properties of QCD, we can do this using gauge invariance. So if we start with a very simple process, so E plus E minus to gamma gamma, just this process, we have two diagrams. So one is the T-channel exchange and one is the U-channel exchange. So we can call them D1 and D2. And we can calculate these using the Feynman rules. So D1 looks like this, D2 looks like this. And we can write this as M mu nu and then the spinors, the photon wave functions. So now gauge invariance means that if we multiply or we do the derivative of M mu nu with either mu or nu and multiply with an on-shell photon, then we should get 0. So this is how you determine gauge invariance. So if we perform this calculation, we just apply the derivative, which can be we can just use the momentum of one photon. Just replace the wave function of one photon with its momentum vector, and have the wave function of the second photon. We get this. So minus this plus this, so it's 0. So very good. We get 0, but only when we add the two diagrams. You can do all these steps by yourself later on if you want to. So if we now have a non-abelian theory like color, we'll have, if we change the order of our generators, we get a non-zero term. So that's what non-abelian means. In this we take the quarks to be in the fundamental representation of the two-3, and the anti-quarks to be in the anti-fundamental representation. So then the current will be 3 times 3, which divides into a singlet and an octet. So we can identify the gluon with this octet here. So the singlet is a photon. And we can generalize our QD vertex to this. So the only difference here is that we have a different field strength, or coupling strength, and then we have the generator for QCD. So if we now go back and do exactly the same calculation, calculate QQ bar goes to glue glue, then we'll obtain the same thing. We have these two diagrams, and we get the generators for the algebra before the two diagrams, but in different order. So we have BA in one and AB in the other. So now if we just change the order of these, we get back exactly what we got in the photon case, but we have this extra term, the FABC term, which is because when we change the order of these, we get this extra term, the non-abelian aspect. So to satisfy our gauge invariance, we still need this to be 0, but in fact we know that the gamma matrix element is 0, so we'll have this extra piece, which is left out. So this can be written like this, and if we just change the order of things a little bit, it looks just like this. So this is the quark anti-quark gluon vertex, and this looks very much like something new. This new thing looks just like a 3 gluon vertex. So it would look like this, 3 gluons. So now we can add a new diagram, which is QQ bar goes to gluon, which then splits into 2 gluons. And this is the expression that we get for this diagram. Now we get back our gauge invariance, we get 0. And in fact, we can even guess what the Lorentz structure would be for this new interaction. If we assume that we have Lorentz invariance, that the vertex is fully antisymmetric, and that we only have one power of the momentum in the vertex, then we can actually get a unique form of the vertex. It will have to look something like this. And now if we compare to our gauge variation, we can even determine the B0. So B0 equal 1. And of course this term, we need the other gluon to be physical, so to be on shell in order to get this term to this. So this means that the gluon is itself charged on QCD. And this is really the fundamental point of QCD as compared to QED. To have full gauge invariance, actually, if we calculate the glue-glue to glue-glue splitting, we see that we also need a 4-gluon vertex. So QCD is much more complicated than QED. You have 2 more vertices, which is a 3-gluon and the 4-gluon vertex. And this can be summarized as the QCD Lagrangian, which is written like this. So it looks exactly like the QED Lagrangian. We have the gauge field interaction, or the gauge fields and the kinetic term. We have the matter term here, matter kinetic term, and then we have the interaction term. But the field strength that we have here has this extra factor due to the non-abelian nature of QCD. So the final rules are these. And there are a couple of things that I would like to point out here. So we have the 3-gluon vertex, which is just given by the completely anti-symmetric guy here. And then we have the 4-gluon vertex. And the 4-gluon vertex actually has 3 different structures. And the reason is that we have 3 different color structures for the 4-gluon vertex, corresponding to what we get if we have insert an intermediate gluon in the S channel, in the U channel, or in the T channel. So whenever we have a 4-gluon vertex in our theory, we'll always need to introduce 3 different terms in our matrix element. So this looks like just one diagram, but we actually have 3 different terms. Okay, so the last part of this lecture, so each lecture is 1 hour, right? And then there's a break.
Please spend only 30 minutes.
Yes, that's right.
Maybe we can ask for questions.
Yes, I'll ask for questions.
I think it has been very good.
Okay, please.
For maybe very students, it was okay. Please ask questions.
You tell the Tevatron observe some excess.
Right.
The compared to background is some very small excess to me.
Yes.
So it cannot be interpreted by some kind of systematic or experimental errors.
Well, so this is a very good question. And in fact, what's really interesting about this excess is that it's been seen by CDF, which is one of the experiments at the Tevatron, but it has not been seen by D0, which is the other experiment at the Tevatron. And if you just look, actually this is, I think they have more data and the excess is still there, so I think it has a little bit higher significance now for CDF than it has here. As you point out, I mean, if you just increase the error bars a little bit on these points here, it looks like there's no excess anymore. I mean, it's just a small fluctuation. But the CDF, they have done what we as theorists, everything that we have asked for as theorists. They have compared to next to leading order calculations, which means a better simulation of W plus JS, which, as you can see here, is really the main background. We were worried about the top, that maybe the top, you see that the top has a kind of shoulder here. And this shoulder is exactly in the same phase as this excess. We were worried that maybe the top should be a little bit higher here. And also this has been looked at very carefully by theorists and by experimentalists, and they have not been able to explain the excess using this. So there are several different ideas for how this might be explained. What the D0 does is they treat the background in a different way. They don't trust their Monte Carlos. CDF has bigger trust in theorists, so they trust more the Monte Carlos. D0 does not trust the Monte Carlos. So what they do is they look at this curve, and then they reweight in every bin. They apply a different weight for every bin. And then they can reweight, so all these backgrounds go exactly through the points. And do this, of course, we can explain away any excess. So there is a tension between CDF and D0. The theorists at Fermilab, where I am, tend to believe more in CDF, but they also can't really explain excess. So I think at this point, since the teleplan is no longer running, we won't get much more data. We're just waiting for the LHC. And it will take a long time before the LHC would be able to see something which is this light. So for a teleplan, it's good that it's light because it means it has high cross-section. For the LHC, it's bad that it's light because the LHC has so much QCD radiation that the background completely covers a signal at this scale. So we might never really know if this is true or not, which would be a very, very sad scenario. At the LHC, you mean?
Yeah, I don't see the reports is that they have not lots of people.
This is.
Yeah.
So have you seen this?
No, they have to also see the W mass and the Z mass peak.
Because before you see the W and Z mass peak, you can't say anything. That's for sure. So that's the first question to ask. Yes.
Can I give a small comment to theory students? Because I noticed that you talked about QQ down to 2 photons.
Yes.
Yeah, and so photon is in the final state. Do you have a talk? No, we haven't talked yet. Maybe. To old fashioned.
Do you want to draw on my computer?
Yeah.
Actually, how do I do that? Is there some good program?
Without having talk, it's too difficult to explain. Go here? Oh, no, I know that's too difficult.
Yeah, no.
No.
It's not.
Yeah, I tried to do it once, and it was so difficult.